4.2465. That's the distance in light years to the closest star that isn't our Sun. Sounds almost manageable, right? Until you do the math. 42 trillion kilometers, 6,700 times farther than Pluto, and our fastest spacecraft, the fastest object humanity has ever built, would need 6,600 years to get there. We're talking longer than written languages existed, and here's the part nobody talks about. We have never, not once, seen that star as it actually is right now. Every single photon arriving from it tonight left more than 4 years ago. That's the nearest one. So what does that actually mean for exploration? Stick with me, because the nearest star turns out to be less of a neighbour and more of a reminder of what the universe will never let us have. If you're new here, hit like and subscribe. Pour yourself something warm, get comfortable, because tonight I'm walking you through exactly what that number means, why the nearest star is far stranger than anyone told you, and why the universe itself may have had a reason for putting it just out of reach. Now, let's ease into it. Part 1. The Friendly Lie of Nearest. Proxima Centauri is 4.2465 light-years away. Write that down on a postcard. Show it to a friend. Read it out loud in a quiet room. It sounds almost polite, does it not? It sounds like a number that belongs on a recipe card or a speed limit sign. It has a decimal point. It has fewer digits than your phone number. It slides off the tongue with the casual confidence of a fact you could memorize in the shower and recite at a dinner party. And yet this friendly, compact, postcard-sized little number is one of the most quietly terrifying measurements in all of science. Because what it actually describes is not a place you can go. It is not even a place you can see as it currently is. It is a boundary, a wall, a kind of physical rule dressed up as a destination. And this is the contradiction I want to open with, the one we are going to be returning to again and again throughout this entire journey. The word we use for Proxima Centauri is nearest. That word, nearest, carries with it every assumption your brain has ever made about closeness. Nearest grocery store, nearest exit, nearest friend. In every one of those cases, nearest means reachable, nearest means accessible, nearest means if you really needed to, you could get there. But when astronomers say nearest star, that word is carrying a weight it was never designed to hold. Because the nearest star, by every practical measure of what human beings can do with machines we have actually built, is already functionally unreachable. It is the closest thing of its kind in the entire universe to us, and it sits behind a barrier that no ship in the history of our species has even begun to cross. That is the friendly lie. And I think the lie works on us because of something very human, something very understandable. Our intuition about distance was forged on the surface of a planet. Every sense of near and far that your brain carries around was calibrated by walking, by running, by throwing rocks, by riding horses and eventually driving cars and eventually boarding airplanes. Every reference frame you own was built inside an atmosphere, and inside that atmosphere, distances behave predictably. A mile is a mile. 1,000 miles is a long drive but a short flight. 10,000 miles is the other side of the planet, which is still, somehow, a place you could stand tomorrow if you really wanted to. Your brain never had to learn what 1 trillion kilometers feels like. It was never asked to. There was no evolutionary advantage to intuiting cosmic scale, because nothing your ancestors encountered required it. So when somebody hands you the number 4.2465 light years, your brain does the only thing it knows how to do. It files that number next to other numbers you have seen. It compares it to the 238,000 miles to the moon, which people have actually visited. It compares it to the distance to Mars, which robots have actually crossed. And because 4.2465 is such a small-looking number, your brain quietly assumes that Proxima must be the next reasonable stop on the same sort of map. It is not. It is not even close to being on the same map. Let me give you the first comparison that begins to break this open. Pluto. You know Pluto. Tiny frozen world on the edge of the solar system, ex-planet, keeper of our collective emotional grievances about scientific classification. Pluto sits, on average, about 3.7 billion miles from the Sun. That is a journey that took the New Horizons spacecraft almost 10 years to complete, and when it got there, it did not stop. It just flew past, waved, and kept going into the dark. Proxima Centauri is roughly 6,700 times farther from us than Pluto is. 6,700 times. Read that again. If Pluto is the outer edge of everything we even vaguely consider home, then the nearest star is almost 7,000 Plutos farther out. And Pluto itself, remember, is already so far away that the fastest spacecraft we have ever sent there took a decade to arrive. This is where we meet our first real traveller in this story, the Parker Solar Probe. This is a machine built by human hands, launched by human rockets, currently hurtling around the inner solar system at speeds that would have seemed like science fiction 1 generation ago. At its fastest, the Parker Solar Probe moves at about 692,000 kilometers per hour. That is roughly 430,000 miles per hour. It is the fastest object our species has ever created. No spacecraft, no bullet, no projectile, no vehicle of any kind has ever moved faster through space than this little probe we sent to skim the outer atmosphere of our own star. And if you pointed the Parker Solar Probe at Proxima Centauri tomorrow morning and told it to just keep going, it would arrive in about 6,600 years. Let that sit with you. 6,600 years is longer than the entire recorded history of human civilization. The oldest writing systems we've ever discovered are not that old. The pyramids of Giza are not that old. If you launched our fastest machine today and asked it to cross the distance to the nearest star, it would arrive after every language currently spoken on Earth had probably died out, after every nation currently in existence had probably fallen, after the map of our own planet had been redrawn dozens of times over, and that is the fastest machine we have. So I want you to start feeling something here. Not fear, not dread, something quieter than that. I want you to start feeling the first hint of a strange, beautiful, unsettling idea, which is that we are already inside a system we cannot physically escape. Not because we are being held here, not because anyone is stopping us, but because the walls of our cell are made of the same stuff the universe itself is made of. The walls are distance, the walls are time, the walls are the speed of light itself, which we will get to in a moment. The nearest star, in other words, is not a destination, it is a boundary condition. It is the edge of what our physics allows us to touch. It is the first thing in the universe that is genuinely, structurally, mathematically outside the reach of any tool we currently know how to build. And here is a small, strange fact that I want to leave hanging in the air as we move forward. We have never, in the entire history of astronomy, seen Proxima Centauri in real time. Not once. Not the most powerful telescope on Earth, not the Hubble, not the James Webb. Every photograph, every spectrum, every measurement ever taken of that star is a photograph of its past. A delayed postcard from 4 years ago. And as we are going to see, that delay is not a flaw in our instruments. It is a feature of the universe itself. Stay with me. Because the nearest thing to us, the closest neighbour we have, is already a kind of ghost. Part 2. The hidden meaning of a light year. So let us talk about what a light year actually is, because I suspect you have been using this word your entire life, without anyone ever really stopping to explain what it is doing. A light year is not a distance. Not really. I mean, technically it measures distance, yes, in the same way that a stopwatch technically measures hands moving around a clock face. But the thing it is actually describing, the thing that makes it such a strange and revealing unit, is time made spatial. It is the distance that light, the fastest thing in the universe, travels in 1 year. And light moves at 299,792,458 meters per second. That is roughly 186,000 miles per second. In the time it takes you to say the word second out loud, a beam of light could circle the entire Earth about 7.5 times. That is the fastest anything is allowed to move in this universe. Not the fastest we have managed so far, not the fastest we have built. The fastest anything is allowed to move, ever, under the rules of physics as we currently understand them. This is not a speed limit like the one on a highway. This is a speed limit like the rules of arithmetic. You cannot break it the way you cannot make 2 + 2 = 5. The universe simply does not permit it. So when we say that Proxima Centauri is 4.2465 light-years away, what we are really saying is this. The fastest thing that exists, the absolute physical limit of speed in the known universe, takes 4.2465 years to cross the gap between us and the nearest star. Light, which we think of as instantaneous in our everyday lives, which crosses a room so quickly that we genuinely cannot perceive the delay, needs more than 4 years to make this particular trip. And that reframes everything. Because the light year is not a measure of how far apart two things are in space. It is a measure of how long causality itself takes to cross that gap. It is a measure of the delay between two places. It is a measure of how out of sync 2 points in the universe are with each other. This is the hidden meaning of a light year. It is a causality interval. It is the length of time during which two places cannot possibly know about each other. And once you start seeing it this way, the entire sky transforms. Because every photon that reaches your eye from a star is a messenger that left its home a long time ago. That photon has been travelling at the maximum allowed speed in the universe, and it has still taken years, or centuries, or millennia, or in some cases billions of years, to arrive at your retina. When you look at the night sky, you are not seeing the universe. You're seeing a reconstruction of the universe assembled from millions of different postcards, each one mailed from a different point in the past. The light from the sun that is warming your skin right now, if you're standing in daylight, left the surface of the sun about 8 minutes and 20 seconds ago. That is how long it takes a photon to cross the 93 million miles between us. If the sun were to suddenly vanish, genuinely disappear from existence, you would not know for more than 8 minutes. You would sit there in what you believed was sunlight, totally unaware, while the physical object producing that sunlight had already ceased to exist. The light from the moon is about 1 1/3 seconds old when it reaches you. The light from Jupiter, depending on where it is in its orbit, can be anywhere from 33 minutes to 53 minutes old. The light from Pluto is more than 5 hours old by the time it reaches telescopes on Earth. And the light from Proxima Centauri, more than 4 years old, every single photon, every time. Think about what that means. The nearest star in the universe to us, the closest stellar neighbour we have, is only ever visible as it was 4 years ago, not as it is now, as it was. If you go outside tonight and point a telescope at the Alpha Centauri region and look carefully enough to pick out that faint red dwarf hiding there, you are not looking at the present. You're looking at a photograph of the past that is travelling through space at the maximum speed the universe allows, and it is still taking over 4 years to get here. This is why astronomy is, in a very real and literal sense, archaeology. Every astronomer, every observatory, every telescope is a time machine pointed backward. The deeper into space you look, the deeper into the past you see. The galaxies photographed by the James Webb Space Telescope are not galaxies as they exist today. Many of them are galaxies as they existed more than 13 billion years ago, back when the universe itself was still young, back when the first stars were just beginning to switch on. Some of those galaxies may not even exist anymore. We are looking at their ancient light long after the objects themselves have collided, merged, or scattered into entirely different structures. And here is the paradox inside all of this, the one I really want you to hold on to. The closer an object is to us, the less current its image seems to feel, because the delay is smaller and therefore easier to ignore. But the closer it is, the more it actually matters whether it is current or not. A galaxy 10 billion light-years away is effectively frozen in deep history anyway. We never expected it to be current. But a star 4 light-years away, that is a neighbour. That is close enough that you feel like you should be seeing it in real time. That is close enough that the delay feels wrong, and the delay is exactly 4.2465 years long. Exactly. Not approximately, not usually, exactly. Every single time, with no exceptions, because the universe does not permit exceptions. No signal, no photon, no piece of information of any kind can cross that gap faster than light. Not radio waves, not gamma rays, not the most advanced communication system any civilization anywhere could ever theoretically build. If the laws of physics as we currently understand them are correct, and every experiment we have ever run suggests they are, then the 4-year delay between us and Proxima is not negotiable. It is not an engineering problem. It is a feature of reality itself. So the universe, it turns out, is never really observed in real time. Not anywhere. Not by anyone. The entire sky is a vast, layered, delayed broadcast, and every object you see is sending its message out of the past. And the nearest one of those messages, the closest voice we could ever possibly hear from another star, is already 4 years late. Which means the word nearest, when applied to Proxima Centauri, already contains within it a guarantee of delay. Proximity in cosmic terms has time baked into it. You cannot be close to something and current with it at the same time once you leave the scale of Earth. The two ideas, near and now, stop overlapping, and that is only the beginning of what this word, nearest, is hiding from us. Part 3. The identity of Proxima Centauri. So let us meet this star, because we have been talking about Proxima Centauri for a while now, and I have not really told you what it is. Proxima Centauri is a red dwarf. Specifically, it is classified as an M5.5 VE star, which is a designation that tells astronomers a whole lot in very few characters. The M means it is a cool, low-mass star, the most common kind of star in the universe. The number tells you where it sits on the spectrum of redness and temperature within that category. The V tells you it is a main sequence star, one that is currently burning hydrogen in its core the way most stars spend the bulk of their lives. And the little E at the end, that is interesting. That E tells you the star shows emission lines in its spectrum, which is a subtle way of hinting at the violent personality we will come back to later. But the basic picture is this. Proxima is small. It is cool. It is dim. It has about 12.5% of the mass of our Sun. Its surface temperature is around 3000 Kelvin, compared to our Sun's roughly 5772 Kelvin. It is dramatically less energetic, dramatically less luminous, and dramatically less visible than the star you're used to seeing in the sky. In fact, Proxima Centauri is so faint that you cannot see it with your naked eye. I want to emphasize this because it is one of the strangest and most counterintuitive facts about our own night sky. The nearest star in the entire universe to our Sun is invisible to the unaided human eye. It sits at an apparent magnitude of about 11.13, which in astronomical terms means it is roughly 100 times too faint to be seen without a telescope. You could stand under the clearest, darkest sky on Earth with perfect eyesight on a moonless night in the middle of nowhere, looking directly at the exact patch of sky where Proxima is located, and you would see nothing. Just stars around it. Just empty black where it is. And contrast that with the stars you do know. Sirius, the brightest star in the night sky, is about 8.5 light-years away, roughly twice the distance of Proxima. But Sirius blazes. It is one of the first things you see when the sky gets dark. Vega, in the summer triangle, about 25 light-years away, bright as a beacon. Betelgeuse, that famous red shoulder of Orion, around 500 light-years away. Still bright enough to dominate a constellation. Rigel, Orion's foot, nearly 900 light-years away. Gorgeous, clearly visible, sometimes outshining Betelgeuse. So you have stars that are twice as far, 6 times as far, 100 times as far, 200 times as far as Proxima, and they are all clearly visible in the sky. And the closest one, the nearest neighbour we have, is hiding, invisible. Not because it is behind anything, not because something is blocking it, but because it simply does not produce enough light to register on the biological detectors you carry in your skull. This is the first great irony of our stellar neighbourhood. The brightest stars we see are not the closest. They are the loudest. They are the show-offs. They are the massive, hot, luminous furnaces that burn themselves out in a few million years and spend that whole time shouting their light across enormous distances. The quiet stars, the stable, steady, long-lived red dwarfs that make up the majority of the galaxy's population, they whisper. And the closest one to us is whispering too quietly for us to hear without help. Proxima was not even discovered until 1915, which is remarkable when you think about it. Humans had been looking at the night sky systematically for thousands of years. We had catalogued thousands of stars. We had built telescopes capable of seeing astonishing detail. And the nearest star to our Sun eluded us until the early 20th century, when a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa, noticed something strange. Innes was studying the Alpha Centauri system, which had long been known to be one of the closest star systems to us. Alpha Centauri A and Alpha Centauri B are two sun-like stars orbiting each other, and they are bright enough that anyone in the southern hemisphere has seen them their whole life. But Innes noticed, through careful observation, a tiny, faint red speck near Alpha Centauri that seemed to share its motion through space. The speck moved across the sky at the same rate in the same direction over the course of years as the bright pair. That shared motion was the clue. Things that move together in space are usually bound together in space. Innes realized this faint red speck was physically associated with the Alpha Centauri system. And when he measured its position more carefully using a technique called parallax, he discovered something extraordinary. This tiny, invisible, anonymous little star was actually closer to us than Alpha Centauri A and B were. Slightly closer, by a fraction of a light year, but closer. Parallax, by the way, is one of the most elegant tools in astronomy, and it is worth taking a moment to appreciate. The idea is simple. As the Earth orbits the Sun, our viewing position shifts by about 186 million miles every 6 months. Nearby stars, when observed from these two different viewpoints, appear to shift slightly against the background of more distant stars. That shift is called parallax, and the size of the shift tells you exactly how far away the star is. It is the same principle that lets your two eyes judge distance, just scaled up to a cosmic level. Your eyes are separated by a few inches. The Earth's two orbital viewpoints are separated by 186 million miles, and that enormous baseline is what lets us measure stellar distances with real precision. When Innes applied parallax to the faint red speck near Alpha Centauri, the math came back undeniable. This star, this quiet little red dwarf, was the closest stellar neighbour we had. It was given the name Proxima, from the Latin word meaning nearest, and that is what it has been ever since, Proxima Centauri, the nearest one. So that is the star we are talking about, a tiny red dwarf, 1/8 the mass of the Sun, producing less than 1% of the Sun's energy. Specifically, about 0.17% of the Sun's luminosity. If you could somehow replace our Sun with Proxima Centauri, the planet Earth would freeze solid almost immediately. The Sun we depend on is, by red dwarf standards, a blazing inferno. Proxima is, by our standards, barely lit. And here is the emotional inversion I want you to sit with as we close out this first act. The closest star to our Sun is one that most of you, even if you have spent your entire life looking up at the night sky with love and attention, have never actually seen. Not once. Not even glimpsed. It is too faint. It is too small. It is too quiet. And yet, it is the nearest. It is right next door, in cosmic terms. It is the closest thing of its kind that the universe has allowed us to have. The nearest star is a ghost, invisible to us in real time because its light takes 4 years to arrive, and invisible to us in any time because it does not produce enough light to register on our eyes regardless of how long we wait. And if the nearest star is already this unreachable, this invisible, this strange, then what exactly are we going to discover when we start asking what it would take to actually get there? Part 4. The Solar System Collapse. I want to come back to Pluto for a second, because I do not think we gave Pluto its due last time. Pluto is, by any reasonable measure, far. It orbits the Sun at an average distance of about 3.7 billion miles, or roughly 39 astronomical units. An astronomical unit, by the way, is just the distance from the Earth to the Sun, about 93 million miles. We use it as a standard yardstick for the solar system because numbers in miles or kilometres get unwieldy very quickly out here. So Pluto sits at around 39 astronomical units from the Sun. The New Horizons spacecraft took about 9.5 years to reach it, travelling at speeds that would have embarrassed every rocket ever launched before that point. And when it got there, it flew past at over 30,000 miles per hour and took some of the most beautiful photographs of a distant world in the history of our species. Hearts on ice, nitrogen glaciers, mountains the size of the Rockies rising out of a frozen nitrogen plain. Pluto is far. Pluto is so far that a radio signal from New Horizons, even now, takes over 7 hours to reach Earth. And Pluto is 6,700 times closer to us than Proxima Centauri. That is the first scale we have to break before we can even begin to think about the nearest star honestly. Because Pluto feels impossibly distant to us. It took most of a decade and billions of dollars and some of the best engineering ever performed to get a flyby probe out there. And Pluto is, in the context of interstellar space, basically our backyard. Let me give you a different way to see this. Voyager 1. You probably know this one. Voyager 1 is a spacecraft that was launched in 1977, almost 50 years ago, and it has been travelling outward from the Sun continuously ever since. It is now the most distant human-made object in the universe. Right now, as you're hearing this, Voyager 1 is approximately 167 astronomical units from the Sun. That means it is more than 4 times farther out than Pluto. It has been leaving for almost half a century, and it has just barely begun to touch what we call interstellar space. If you took Voyager 1, which has been running for nearly 50 years, and asked how far along it is on the journey to Proxima Centauri, the answer is so small it is almost comical. Voyager 1 has covered about 0.003% of the distance to the nearest star, 0.003%, in 50 years. This is the scale collapse I want you to feel. Our entire solar system, the entire bubble of influence around our Sun, the region where planets orbit and comets loop, and the solar wind pushes outward against the pressure of interstellar space, is a tiny, tiny thing compared to the gap between us and the next star. There is a boundary out there called the heliopause, which is the edge of the Sun's influence, the place where the outward flow of solar wind is finally overcome by the pressure of the surrounding galactic medium. Voyager 1 crossed that boundary in 2012, after 35 years of travel, and even now, having crossed into true interstellar space, it is still unimaginably closer to the Sun than to any other star. So picture the solar system for me. Really picture it. The Sun at the centre. Mercury, Venus, Earth, Mars close in. The asteroid belt. The gas giants, Jupiter and Saturn, Uranus and Neptune, each with their own complex systems. Then Pluto and the Kuiper belt, out there past Neptune, a ring of frozen worlds. Then the heliopause, the edge of our solar bubble. Then beyond that, a vast, almost empty region called the Oort cloud, which is a theoretical shell of comets extending maybe a full light year out from the Sun. And even the Oort cloud, even that outermost, most speculative edge of our solar system, ends long before Proxima Centauri begins. There is a gap, a void, a stretch of essentially empty space between where our solar system ends and where the next stellar system begins, and that gap is enormous. This is why I keep insisting that the nearest star is where our system ends, because it genuinely is. Proxima Centauri is not part of our neighbourhood in any meaningful sense. It is the beginning of the next neighbourhood. It is on the other side of a gulf that nothing we have ever built has even begun to cross. Let me try to give you a model that might actually fit in your head. If you shrink the Sun down to the size of a basketball, then Earth becomes a peppercorn, about 26 metres away from that basketball. Jupiter becomes a chestnut, about 135 meters away. Pluto becomes a barely visible grain of dust, about 1 kilometer away. That is the entire visible solar system, the whole thing you grew up drawing in school, fitting inside 1 kilometer. At that same scale, Proxima Centauri is another basketball, roughly 7,000 kilometers away. That is farther than New York to Tokyo, farther than London to Buenos Aires. 2 basketballs, sitting on opposite sides of the planet with nothing but empty black in between them. That is what interstellar space actually is. That is what the gap between stars actually looks like when you scale it properly. It is not a little extra distance beyond Pluto. It is an entirely different regime of emptiness. The solar system is crowded, relatively speaking. Planets are close to each other, in the grand scheme of things. Moons are close to planets. The whole structure is dense and active and full of objects. But once you leave the solar system, you enter a place where there is almost nothing. No planets, no moons, no asteroids, no significant objects of any kind. Just hydrogen atoms, maybe 1 or 2 per cubic centimetre, drifting around in the vast, dark, cold medium between stars. Space is mostly distance, not objects. Space is mostly emptiness, with occasional points of light scattered through it. And this is where human intuition finally, completely fails. Because nothing in your everyday life prepares you for this kind of emptiness. When you walk outside and look around, you're always inside something. A room, a building, a city, a forest, a field. Even when you're in the middle of the ocean, you have air around you, clouds above you, water beneath you. You're embedded in a rich, dense, continuous environment full of things. Interstellar space is not like that. Interstellar space is mostly nothing, and the nearest star is on the far side of an almost unimaginable amount of that nothing. So when we say that Proxima Centauri is the nearest star, what we really mean is that the solar system collapses before you get there. Everything familiar ends. Everything we have ever touched or photographed closely ends. And then, beyond all that, beyond the edge of what our influence reaches, there is a tiny red dwarf, invisible to the eye, sitting in its own little bubble of reality, 4 years of light away. The nearest star, in other words, begins where our system ends, and the gap between those 2 points is where human exploration has not yet been able to write a single sentence. Part 5. Human Travel Reality Check. So now we have to ask the obvious question. If we actually wanted to get there, how would we do it? And how long would it take? Let us come back to the Parker Solar Probe. This is our champion. This is the machine we hold up as the fastest thing humanity has ever built. It hit its top speed of about 692,000 kilometers per hour by slingshotting close to the Sun, using the Sun's gravity to accelerate itself to speeds that no spacecraft had ever reached before. That is roughly 0.064% of the speed of light. 64 thousandths of 1%. If you could somehow redirect the Parker Solar Probe toward Proxima Centauri at that top speed, and if it could somehow maintain that speed all the way there, which it cannot, but let us pretend, it would take approximately 6,600 years to arrive. 6,600 years. I want to give you some perspective on that number, because it is easy to hear it and not really feel it. The pyramids of Giza were built around 2600 BCE, which is roughly 4,600 years ago. So if a civilization roughly as advanced as ancient Egypt had launched the Parker Solar Probe at the time they were building the Great Pyramid, and that probe had been travelling continuously ever since, it still would not have arrived at Proxima Centauri. It would have about 2,000 more years to go. The oldest known written language, cuneiform, dates back about 5,300 years. So if a civilization at the very dawn of literacy had launched a Parker Solar Probe speed mission to the nearest star, we, today, would still be waiting for it to arrive. And we would have to wait more than 1,000 years longer. This is not a flaw of the Parker Solar Probe. This is a flaw of the entire concept of crossing interstellar distances with any technology that operates on remotely comparable speeds. The journey to the nearest star, with our best current technology, is longer than civilization itself. It is longer than language. It is longer than any institution, any government, any nation, any empire that has ever existed on Earth. Think about what it would take to sustain a mission across that kind of time. You would need a ship that could operate for 6 millennia without catastrophic failure. You would need people, or their descendants, who maintained a purpose and a memory across more than 200 generations. You would need a civilization back on Earth that remembered why it had launched the mission in the first place, and cared enough to still be listening when the results came back. You would need political continuity, scientific continuity, cultural continuity across a time frame during which every known human institution has, historically, risen and fallen multiple times over. It is not an engineering problem, it is a civilizational one, and we have no examples anywhere in our history of any human project being sustained across even a fraction of that duration. But wait, you might say, let us do better. Let us not use chemical rockets. Let us use something smarter. And you would be right to push back, because chemical rockets are, physically speaking, near the edge of what they can do. A chemical rocket works by burning fuel and expelling it out the back end. The speed of that expelled gas, called exhaust velocity, is limited by the energy of the chemical reaction. There is a ceiling. We have more or less reached it. The fastest chemical rockets we can conceivably build are not going to be much faster than the ones we already have. So could we use nuclear propulsion? Sure. Nuclear rockets are theoretically more efficient than chemical rockets. They can achieve higher exhaust velocities. Designs have been sketched out for decades, but the improvement is incremental. A nuclear-powered interstellar mission might cut the travel time to Proxima Centauri down from 6,000 years to maybe 1,000 years, or a few hundred years if we are generous with the engineering assumptions. Still longer than any human civilization has ever lasted. Still effectively impossible. What about antimatter? What about fusion? What about the exotic, high-energy concepts that populate the margins of serious physics journals and the centers of science fiction novels? Could we get to 10% of the speed of light? Could we get to 50%? Could we get to 90%? In principle, yes. In principle, nothing forbids it. If you could build a spacecraft that accelerated at 1 gravity, meaning it accelerated at the same rate that the Earth's surface pulls objects downward, for a long enough period, you could in theory approach a significant fraction of the speed of light. The problem is not acceleration. The problem is energy. To accelerate a ship the size of, say, the International Space Station to 10% of the speed of light, you would need an amount of energy roughly equivalent to the entire global annual energy production of human civilization, for just that one ship. And that is assuming perfect efficiency, which nothing in the real world ever provides. The actual energy requirements would be vastly higher, and then you would need an equivalent amount of energy to slow the ship down at the other end, because otherwise you would just fly past Proxima Centauri at 10% of the speed of light and never stop. This is where the breakthrough starshot concept comes in. It is a serious proposal, funded by serious people, aimed at actually getting a probe to Proxima Centauri within a human lifetime. The idea is elegant. You give up on the notion of sending a big spacecraft. Instead, you send something tiny, a gram-scale probe, a chip the size of a postage stamp, attached to a light sail the size of a bedsheet. Then, from Earth, you fire an enormous ground-based laser array at the sail, pumping so much energy into it that the probe accelerates to about 20% of the speed of light in the span of a few minutes. At that speed, the probe would reach Proxima Centauri in about 20 years, and then, because it has no way to slow down, it would fly past the entire star system in a matter of hours, collecting what data it could, beaming results back to Earth at the speed of light. Those results would take another 4 years to arrive, so a mission launched today would produce its first data around 2050 or so, at the earliest, assuming everything works perfectly, which it never does. And even this heroic, gram-scale, probably not going to happen anytime soon mission does not give us a person at Proxima Centauri. It gives us a glimpse, a flyby. A few hours of data about a star system we have been dreaming of for centuries. Nobody stops, nobody lands, nobody stays. This is the reality check. Even our most ambitious, most optimistic, most generously funded concepts for interstellar travel do not give us the ability to actually go to Proxima Centauri in any meaningful sense. They give us at best a chance to send a tiny machine past it at a fraction of the speed of light and collect some data on the way through. And I want to be honest with you, I know some of you are going to push back on this. I know some of you are going to say, well, what about future technology? What about things we have not invented yet? What about warp drives and wormholes and Alcubierre metrics and all the exotic physics that gets discussed in theoretical papers? And here is what I have to say about that. The reason we keep hitting this wall is not because we have not been clever enough. It is not because we have not invested enough. It is because the wall is made of physics, not of engineering. Physics. The speed of light is not a technical limitation. It is a property of the universe, baked into the structure of space-time itself. Every experiment we have ever performed, every observation we have ever made, every test of relativity we have ever run, has confirmed that this limit holds, absolutely, universally, without exception. So when we say that even the fastest possible travel cannot really bridge the distance to the nearest star, we're not talking about a failure of imagination. We're talking about a feature of reality. Speed improvements, no matter how aggressive, no matter how creative, do not remove the fundamental fact of interstellar separation. They just change the flavour of the problem. At slow speeds, the problem is civilizational duration. At high speeds, the problem is energy. At relativistic speeds, the problem is deceleration. At theoretical speeds beyond light, the problem is that we have no physics that permits such speeds to exist. The nearest star, no matter how we approach it, remains on the other side of a barrier. Which brings us to what that barrier actually is. Part 6. The speed ladder of impossibility. Let me run you through the ladder, because I think seeing all the speeds stacked up against each other, in order, makes the scale of this problem click in a way that numbers alone never can. A commercial airliner travels at about 900 kilometers per hour. That is roughly 560 miles per hour. If you could somehow fly a commercial jet to Proxima Centauri, assuming it never ran out of fuel, never needed maintenance, and could somehow operate in a vacuum, it would take about 5 million years to arrive. Not 1,000. Million. 5 million years is longer than our species has existed. Homo sapiens has been around for something like 300,000 years. 5 million years takes you back to before we were even recognizably human. A chemical rocket travelling at its typical interplanetary speed, say 40,000 kilometers per hour, would take about 114,000 years. Still longer than agriculture. Still longer than cities. Still longer than any civilization. Voyager 1, moving at about 61,000 kilometers per hour, would take about 73,000 years. New Horizons, moving a bit slower, about 80,000 years. The Parker Solar Probe, our speed champion, would take about 6,600 years. A theoretical nuclear pulse propulsion spacecraft, using the old Project Orion designs that envisioned detonating small nuclear bombs behind a heavily shielded pusher plate, might reach a few % of the speed of light. That would get you to Proxima in maybe 100 to 300 years, still longer than most human lifetimes, though now within the realm of a multi-generational mission. A theoretical fusion rocket, using controlled nuclear fusion as its propulsion source, might reach 5 to 10% of the speed of light, getting you there in 40 to 80 years. A single human lifetime, barely. A crew launched at 20 could arrive at 60, assuming everything worked perfectly, which it almost certainly would not. An antimatter rocket, if we could ever produce antimatter in useful quantities, which we currently cannot, and which we have no known way to produce at scale, might reach 25 to 50% of the speed of light. That would cut the trip to around 10 to 20 years, and the Starshot laser sail concept, at 20% of the speed of light, would make the trip in about 20 years one way, plus the 4.24 years of communication delay at the end. Now look at that ladder. Look at the span it covers, from 5 million years at the bottom to 20 years at the top. That is a factor of 250,000 between our slowest realistic travel method and our most ambitious theoretical one. And yet the distance does not change. The 4.2465 light years between us and Proxima stays exactly the same no matter how fast we travel. It is the speed, not the distance, that is doing the work in all of these calculations, which reveals something important about the nature of this problem. It is exponential. The gap between what we can do now and what we need to do to really travel between stars is not a small gap. It is not a gap you close with incremental improvements. It is a gap that requires you to invent entirely new physics, entirely new engineering, entirely new energy sources, just to make a dent in it. And even then, even if you achieve a significant fraction of the speed of light, you run into new problems. At 10% of the speed of light, a single grain of interstellar dust, a dust grain so small you cannot see it without a microscope, hits your spacecraft with the energy of a small explosion. At 20% of the speed of light, that same dust grain becomes a miniature bomb. At 50%, individual hydrogen atoms in the interstellar medium become cosmic rays that will fry your ship's electronics and kill any crew you have on board. The faster you go, the more the universe itself becomes your enemy. And I want to emphasize this part because it is often overlooked. Acceleration is not the solution people sometimes think it is. If you have enough energy to accelerate to 20% of the speed of light, you also need enough energy to decelerate at the other end. Otherwise, you just fly through the target system in a few hours, and the deceleration problem is, in many ways, harder than the acceleration problem, because you cannot rely on ground-based lasers from Earth to slow you down. You have to carry your deceleration fuel with you, which means you have to accelerate that fuel, which requires more fuel, which requires more acceleration, and now you are in what rocket engineers call the tyranny of the rocket equation, where your fuel requirements grow exponentially with your mission speed. This is why the Starshot concept is so clever and so limited at the same time. By giving up on deceleration entirely, by accepting that the probe will just blast through the Proxima system at 20% of the speed of light and never stop, the mission becomes theoretically feasible, but it also becomes a flyby, a glimpse, a wave from across the street. And here is the deeper truth that this ladder reveals. No matter how far you climb up it, no matter how fast you go, the nearest star remains permanently on the other side of a barrier. Because fast is not the same as arriving. You can go faster and faster and faster, and every increment of speed makes the trip shorter, but it does not make the trip easier in any fundamental sense. It does not bring the star closer. It does not reduce the amount of universe you have to cross. It just changes how long you have to spend crossing it. The nearest star, in other words, cannot be reached by being fast. It can only be reached by either being patient across geological timescales, which we cannot do, or by approaching the speed of light itself, which requires energy we do not have. And in neither case do you actually arrive as yourself. In the slow version, you arrive as someone's descendant, many generations removed from the people who launched you. In the fast version, you do not arrive at all. You just pass through. The improvements we can imagine, even the wildest ones, do not remove the interstellar separation reality. They only dress it in different clothes. The wall is still there. The wall is always there. And the wall is made of light. Part 7. The photon problem. Let us talk about light. Really talk about it. Because I have been using the word photon casually for a while now, and I think we need to slow down and look at what a photon actually is, because it turns out that photons are strange in ways that will change how you think about the whole universe. A photon is a particle of light. It is also a wave, depending on how you look at it, which is one of the quietly unhinged facts about quantum mechanics that we have all learned to shrug off. But let us bracket that for now. For our purposes, a photon is a messenger. It is a tiny packet of electromagnetic energy that leaves a source, travels through space, and eventually hits a detector. That detector might be the retina of your eye, or a camera sensor, or the mirror of a space telescope. Whatever it is, When the photon arrives, it delivers a message. And that message is information about where the photon came from. Every photon that reaches us from Proxima Centauri is a 4.2465-year-old messenger. That is not a metaphor. That is literally what it is. The photon left the surface of Proxima, started travelling across interstellar space at the speed of light, and has been in transit ever since. 4 years, 3 months, give or take a few days, moving at the fastest speed the universe allows, and it still took that long to arrive. But here is where it gets genuinely strange. From the photon's own perspective, if photons can be said to have a perspective, the trip took no time at all. I need to explain that, because it is one of the weirdest and most beautiful consequences of special relativity. Einstein showed us, over 100 years ago now, that time and space are not independent of each other. They are woven together into a single fabric called space-time. And when you move through that fabric, something very counterintuitive happens. The faster you move through space, the slower you move through time. This is not a philosophical claim. It is a measurable, experimentally confirmed fact about how the universe works. We check it every day. The GPS satellites in orbit around Earth have to correct for time dilation continuously, because their speed relative to the ground causes their onboard clocks to tick slightly differently from clocks on the surface. If we did not correct for that, GPS navigation would drift out of accuracy within hours. Now, the equations of relativity tell us something dramatic about what happens as you approach the speed of light. As your speed gets closer and closer to light speed, your experience of time slows down more and more. At exactly the speed of light, time stops. From the perspective of a photon, no time passes between emission and absorption. A photon that leaves Proxima Centauri and hits your eye 4 years later, from your perspective, experiences zero time. From its perspective, the trip is instantaneous. It is emitted and absorbed in the same moment. This is what physicists mean when they say light travels along what are called null geodesics. The photon's proper time, its internal experience of duration, is zero. It is the only object in the universe that does not experience time, because it is the only object in the universe that moves at the maximum speed. So you have this strange asymmetry. From your perspective, photons from Proxima are ancient. They are 4 years old. They are postcards from a past version of that star. But from the photon's own perspective, it never aged. It was born on Proxima and delivered to your eye in a single timeless moment. And this is why astronomy is, fundamentally, a time-delayed perception system. Everything you see in the sky is a photograph of the past, because every photon that reaches you has been in transit for some amount of your time, even if it experienced no time of its own. Your eyes, your telescopes, your radio dishes, your infrared cameras, they are all receiving delayed signals. They're all looking backward. Let me paint you the picture. The telescope on top of a mountain is a time machine, not metaphorically, literally. When a telescope points at a star 100 light-years away, it is collecting photons that left that star 100 years ago. The star as it exists today, this moment, is invisible to that telescope. The star as it existed a century ago when those photons began their journey is what appears in the image. If the star has changed over the last 100 years, if it has brightened or dimmed or shifted position, or even exploded, the telescope will not know. It cannot know. The information has not arrived yet. This is why, when astronomers say they are looking at something 10 billion light-years away, they are also saying they are looking 10 billion years into the past. The deeper we look, the further back in time we see. The James Webb Space Telescope, with its ability to see extremely distant galaxies, is really an instrument for observing the early universe. It is showing us galaxies as they existed when the universe was maybe 3 or 4% of its current age. Many of those galaxies may no longer exist in any recognizable form. They have had more than 13 billion years to evolve, merge, or scatter. What we see is a snapshot from their ancient past, and the universe of their present is completely hidden from us. So the whole universe becomes a kind of layered memory, a cosmic memory stream, if you will. Every time you look up at the sky, you're looking at a different depth of history, depending on how far away each object is. The moon is a little over a second old. The sun is about 8 minutes old. The outer planets are hours old. The nearest stars are years old. The stars in our own galaxy are up to hundreds of thousands of years old. Nearby galaxies are millions of years old. Distant galaxies are billions of years old. And the cosmic microwave background, the faint radio hiss that fills the sky in every direction, is light from when the universe was only 380,000 years old. That light has been travelling for more than 13 billion years to reach us. Resolution and historical depth in astronomy are the same thing. When you look closer, you also look more recently. When you look farther, you also look older. They cannot be separated. They are two sides of the same coin. And this is where we arrive at the philosophical implication that I want you to sit with. Reality, at least as we can perceive it, is always delayed. There is no such thing as simultaneous observation across cosmic distances. We are never actually seeing anything as it is. We are always seeing it as it was. Which brings us back to our central thread. The nearest star is already a historical object. It is not a present object. When we look at Proxima Centauri tonight, through whatever instrument we use, we are not looking at what is happening there now. We are looking at what was happening there 4 years ago. The star we are describing, the star we are measuring, the star we are pointing our telescopes at, is a star from the past. It is frozen in our perception, in a version of itself that no longer exists. The Proxima Centauri of right now, the star as it exists in this very moment, is unknowable to us, unreachable, hidden behind 4 years of light travel time. And that is true not just of Proxima, that is true of every star, every galaxy, every planet outside our own. The universe, as we perceive it, is a universe of delayed ghosts. Part 8. The communication trap. So let us imagine for a moment that we succeed. Let us imagine that somehow, against all the odds, we get a probe to Proxima Centauri. Or better yet, let us imagine that there is already someone there, a civilization, a society of some kind, another intelligence, living on one of the planets we think are orbiting that faint red dwarf. And let us say we want to talk to them. How would that conversation actually go? Well, the first thing to understand is that any signal we send, whether it is a radio transmission, a laser pulse, a modulated beam of any kind, travels at the speed of light. That is the fastest communication medium that the universe allows. There is no faster option. There is no subspace channel, no hyperwave, no quantum telegraph that can beat the speed of light. Every form of information transfer, no matter how sophisticated, is bound by this limit. So if I send a message to Proxima right now, at this moment, that message will arrive there in 4.2465 years. And if the recipients respond immediately, their response will take another 4.2465 years to come back to me. That is a round trip of about 8.5 years, minimum. Think about what that means for a conversation. I ask a question in 2026. The question arrives in 2030. The response is sent back immediately. It arrives in 2034. One exchange, 8 years and 6 months. That is not a conversation. That is barely even a correspondence. And the problem gets worse when you realize that any meaningful exchange of ideas requires more than one round. I ask a question. They answer. I follow up. They clarify. I build on their clarification. They respond to my new question. Each step is more than 8 years. A single complex discussion, the kind that might happen between two humans over a cup of coffee in 20 minutes, would take decades to unfold across the interstellar medium. A research collaboration might take centuries. This is what I call the asynchronous civilization problem. Any two civilizations separated by interstellar distances cannot have a synchronous relationship. They cannot coordinate in any real-time sense. They cannot govern together. They cannot respond to each other's crises. They cannot share discoveries as they happen. They can only send messages and wait, and wait, and wait. Imagine for a second what this does to every kind of human institution. Science, for example, depends heavily on rapid iteration. One researcher publishes a result, others read it, test it, build on it, challenge it. The whole process of scientific progress depends on a kind of distributed, ongoing conversation where ideas bounce back and forth quickly enough that they can evolve. Now imagine doing science across an 8-year round trip. By the time you get a response to your question, you have already moved on. The person you asked may have died of old age. The experiment they were commenting on may have been replaced by entirely new paradigms. Government is the same, law is the same, diplomacy is the same. All of these institutions depend on communication happening at roughly the speed of human cognition. Take that away, replace it with a near-decade delay, and the institutions collapse. There is no way to negotiate a treaty when each round of proposals takes 8 years. There is no way to form a unified government across 2 star systems when you cannot even pass a simple law in less than a human lifetime. This is what I mean by the interstellar fax machine reality. Any communication between stars is more like sending a letter by sea in the 18th century than making a phone call. You write your message, you send it. You wait years for a reply. Maybe the reply comes, maybe it does not. Maybe by the time it arrives, the situation you were writing about has completely changed, and your correspondent's response is answering a question you no longer care about. Now, I know some of you are going to think, okay, but what about advanced civilizations? What about civilizations so much older and smarter than us that they have figured out some workaround? Some clever way to beat the speed of light that we just have not discovered yet? And here is the hard, strange truth. Even advanced civilizations, no matter how advanced, cannot bypass this limit. Not unless our entire understanding of physics is wrong in some fundamental way. The speed of light is not an engineering limitation. It is not something you overcome with cleverness. It is a feature of the structure of space-time itself. Breaking it would require breaking causality. It would require allowing effects to precede causes. It would require a universe that does not make sense, because a universe where information can travel faster than light is a universe where you can receive an answer before the question is asked, and that kind of universe cannot exist in any coherent form. So even if there are civilizations out there that have been around for millions of years, that have technology we cannot even imagine, that have solved problems we have not yet encountered, they are still stuck in the same trap. They cannot talk to their neighbours in real time either. They cannot coordinate with distant colonies. They cannot share discoveries across interstellar distances as they happen. Any interstellar civilization is necessarily an asynchronous civilization, a loose confederation of mostly independent star systems, connected by delayed, fragmentary communication. Intelligence does not overcome the light speed limit. It just learns to live with it. And this is what our central thread keeps pointing to. The nearest star cannot participate in real-time existence with us. Not in any meaningful sense. We cannot have a present moment with Proxima Centauri. We cannot share a now. The best we can do is exchange delayed messages across a 4-year gap, and even that we have never actually done, because we have never sent or received a signal from anyone there. The nearest star, in terms of shared experience, is further away than any number can really express, because it is not just distant in space, it is distant in time, and in the universe we live in, those two kinds of distance cannot be separated. Part 9. The Vanishing Star Thought Experiment. Let me ask you something strange. What if Proxima Centauri disappeared right now? Not went supernova, not exploded, just vanished. Gone, removed from the universe as if it had never been there. Blink, done. How would we know? The answer, and this is the part that I want you to really feel, is that we would not know. Not immediately. Not for more than 4 years. The light that is arriving at our telescopes tonight left Proxima in 2022. It has been in transit ever since, crossing that enormous interstellar gap at the maximum speed the universe allows, and it does not know, cannot know, whether the star that produced it still exists. The light is just travelling. It is carrying information about the state of Proxima in 2022 and nothing else. So if Proxima Centauri disappeared right this instant, at the moment you are hearing this sentence, we would continue to see it in our telescopes for the next 4 years and 3 months. Every observation we made during that time would suggest a perfectly normal red dwarf. Astronomers would track its motion, measure its spectrum, analyse its flares, and none of it would give any hint that the star had already been gone for years. Only when the last photon arrived, the one that left just before the disappearance, would the darkness finally catch up to us. Suddenly, the spot where Proxima had been in our sky would go quiet. The spectrum would go blank, and we would know. But by then, the event would already be 4 years in our past. Whatever caused the disappearance, whatever response we might have wanted to have, would already be too late by 4 years. Our reaction would be 4 years delayed to an event that had already happened. This is the cosmic lag effect, and it applies to everything, not just to Proxima, to every object in the universe. When a star somewhere 1,000 light years from here goes supernova, we do not see it until 1,000 years later. The explosion is ancient by the time we observe it. The shockwave has been propagating outward for a millennium. The remnants have cooled. The surrounding interstellar medium has been reshaped. And we, down here on Earth, are just now learning that the event occurred. In 1987, astronomers observed a supernova called SN 1987A in a nearby galaxy called the Large Magellanic Cloud. That galaxy is about 160,000 light-years away, which means the supernova, the actual explosion of that star, happened about 160,000 years ago. We saw it in 1987 because that is when the light finally reached us. But the event itself was already prehistoric by the time we noticed it. The star had been dead for longer than our species has existed. That is the cosmic lag. That is the time delay built into every observation of everything that is not in our immediate neighbourhood. The universe we see is not the universe that is. It is the universe that was, layered in various depths of pastness depending on how far each thing is from us. And here is where the really strange philosophical implications start to peek through. There is no universal present moment. There is no cosmic now. The idea that all events in the universe are happening at the same time, that there is a single flowing moment of the present that applies equally everywhere, turns out to be false. Or at least it is false in any operational sense that matters for observation and communication. Different observers in different places have different presents, and they cannot synchronize those presents because any attempt at synchronization requires communication, and communication takes time. Einstein's theory of special relativity goes even further than this. It tells us that simultaneity itself is not absolute. Two events that appear to happen at the same time from one observer's perspective may appear to happen at different times from another observer's perspective, if that observer is moving at a different velocity. This is called the relativity of simultaneity, and it is one of the most philosophically disruptive ideas in modern physics. I do not want to get too deep into the mathematics of relativity here, because it would take us far afield, but I do want you to sit with the core idea. The present moment is local. It only applies to you, in your specific place, at your specific time. It does not extend across the universe. It does not even extend to the nearest star. Proxima Centauri has its own now, which is not accessible to us. Our now is not accessible to it. The two nows are separated by 4 years and 3 months, and that separation cannot be closed. So when we ask the question, what is happening at Proxima Centauri right now, we are asking a question that has no answer, not because we do not know the answer, but because the question itself is ill-formed. There is no right now that connects here and there. There are only our observations of what happened there 4 years ago, and Proxima's observations, if it were observing us, of what happened here 4 years ago. The two perspectives are forever out of sync, and this, I think, is the most profound and unsettling implication of the distance to the nearest star. It is not just that we cannot go there. It is not just that we cannot communicate with them in real time. It is that there is no real time in which to communicate. The universe itself does not support the kind of simultaneous existence that we naively assume. We are all, every one of us, every star, every galaxy, every civilization, locked into our own local pockets of time, connected to each other only by delayed signals that take years or centuries or millennia to cross the gaps between us. The nearest star, under this framing, can already be gone. It may not be there anymore. The light we see is old, and old light tells old stories. There is no way to know from where we stand whether Proxima Centauri still exists in any current sense. We can only know that it existed 4 years ago, and we have to wait for the light of the present to arrive, which it will not, because by the time it arrives, it will have become the light of the past. The nearest star exists for us only as a ghost made of old photons, a ghost that might, for all we know, already have ceased to be. Part 10. Proxima as a violent star. Here is the thing about Proxima Centauri that nobody tells you when they first introduce it as our nearest neighbour. It is angry, not in any metaphorical sense. I mean that this star, this quiet, dim, seemingly gentle little red dwarf, is one of the most violent stars in our local neighbourhood. It is classified as a flare star, which in astronomical language means that it periodically undergoes sudden, enormous outbursts of energy. Massive releases of stellar radiation that brighten the star by factors of tens or hundreds within minutes, blast plasma outward at tremendous speeds, and bathe the surrounding space in hard radiation. And these flares are not rare events. They happen all the time. Proxima Centauri flares more frequently than any star comparable to our Sun. It has been observed to flare dozens of times per day during active periods. And some of these flares are not ordinary. Some of them are super flares, releases of energy so massive that they would make our Sun's largest historical eruptions look like small hiccups by comparison. In 2019, astronomers observed a flare from Proxima Centauri that released more than 100 times the energy of the largest flares ever recorded from our Sun. 100 times. The Carrington event of 1859, the most powerful solar flare in recorded history, disrupted telegraph systems across the world, caused aurora displays visible at tropical latitudes, and would, if it happened today, probably cause hundreds of billions of dollars in damage to our electrical infrastructure. And the Carrington event was small compared to what Proxima regularly does. So why is Proxima so angry? The answer has to do with its internal structure. Red dwarfs are small, but they are also fully convective, meaning that the plasma in their interior churns all the way through the star, from the core to the surface, in a constant, turbulent, boiling motion. This churning drives incredibly complex magnetic field dynamics. Magnetic field lines get twisted, tangled, wound up like rubber bands being knotted by an invisible hand, and eventually those tangled field lines snap. When they snap, they release enormous amounts of energy, and that energy escapes the star in the form of a flare. Our Sun does this too, of course, but our Sun is larger and its structure is different. It has a radiative zone in its interior where the magnetic dynamics are calmer. Its flares are less frequent, less violent, and more predictable. Proxima, by contrast, is a roiling magnetic furnace that is constantly building up and releasing enormous stresses in its magnetic fields. What this means for anyone or anything in the vicinity of Proxima Centauri is that the radiation environment is extreme and unpredictable. One moment the star is relatively quiet. The next moment, without warning, it blasts out a flare that could deliver a lethal dose of X-rays and ultraviolet radiation to any unprotected surface within a few million kilometers. And because Proxima's habitable zone, the distance at which a planet could have liquid water on its surface, is very close to the star, much closer than Earth is to the Sun, any planet in that zone would be bathed in these blasts directly. Let me put this in context. Our Sun, as violent as its occasional flares can be, has a relatively stable luminosity. It varies by a fraction of a percent over the solar cycle. Life on Earth depends on that stability. If the sun's output varied by factors of 10 or more on random, unpredictable timescales, complex life as we know it could probably not exist here. The evolutionary clock of biology needs a stable energy source. Our sun provides that. Proxima does not. Proxima's output varies wildly. Its flares can double or triple or multiply by 100 the star's brightness on timescales of minutes. Any planet orbiting in Proxima's habitable zone would experience radiation levels that swing by enormous factors, constantly, unpredictably, throughout its entire existence. And there is another problem: the stellar wind. Our sun produces a steady outflow of charged particles called the solar wind, which creates the heliosphere and shapes the environment of the solar system. Proxima produces a stellar wind too, but its wind is much more intense, especially during flares, and it is directed at any nearby planets with extraordinary force. Over long timescales, this wind can strip away planetary atmospheres, tearing them off into space, leaving the planetary surfaces exposed directly to the radiation environment. This is what I mean when I say proximity does not equal safety. Proxima Centauri is close, but close to Proxima is not a safe place to be. It is a place of constant radiation, constant atmospheric erosion, constant magnetic storms. Our sun, as mighty and occasionally angry as it can be, is a gentle parent by comparison. Proxima is a different kind of star entirely, one that would sterilize any unshielded surface on a regular basis. And this is why, when we return to our central thread, we have to acknowledge that the nearest star, the one we sometimes romanticize as a possible second home, is physically hostile despite being our closest neighbour. Being closest does not mean being welcoming. Proxima Centauri is not a friendly refuge waiting for us across an impossible distance. It is a violent, unstable, radiation-blasting object that would be as dangerous to visit as it is impossible to reach, which makes the planets that do orbit it all the more interesting. Part 11. Proxima b, the Broken Earth Candidate. In 2016, astronomers announced a discovery that electrified the world. A planet had been detected orbiting Proxima Centauri, not a gas giant, not a distant frozen ice world, a rocky planet roughly the size of Earth, orbiting in the star's habitable zone. They called it Proxima b. The detection was made using a technique called radial velocity, which measures the tiny wobble that a planet induces in its parent star as they both orbit their common centre of mass. Even though the planet itself is too small and too dim to see directly, its gravitational tug on Proxima produces a detectable back-and-forth shift in the star's spectrum, and from that shift astronomers can calculate the planet's mass, orbital period, and distance from the star. What they found was remarkable. Proxima b has a minimum mass of about 1.17 times Earth's mass. Its orbital period is about 11.2 days, meaning a year on Proxima b lasts a little over a week and a half in Earth time, and its distance from Proxima puts it squarely within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planet's surface. For a brief, heady moment, it looked like we had found it. An Earth-like planet at the nearest possible location. A world that might have oceans, continents, atmospheres, maybe even life. Right next door in cosmic terms. A real target for future exploration. A real candidate for a second home. But the enthusiasm had to be tempered quickly, because the more astronomers studied Proxima b, the more complicated the picture became. First, there is the tidal locking problem. When a planet orbits very close to its star, as Proxima b does, the gravitational interaction between planet and star tends to slow the planet's rotation until one face permanently points toward the star and the other face permanently points away. This is called tidal locking, and it is almost certainly the situation on Proxima b. One side of that planet is in perpetual day. The other side is in perpetual night. There is no day-night cycle as we experience it. There is only the bright side and the dark side separated by a thin ring of perpetual twilight along the terminator, the boundary line between them. What would such a world be like? The The bright side would be superheated, with temperatures possibly reaching the boiling point of water depending on the atmosphere. The dark side would be frozen solid, so cold that most gases would condense out of the air and collect as ice. The only potentially habitable region, if any exists, would be the narrow twilight zone along the terminator, where temperatures might be moderate enough to support liquid water. But even that region would be a strange and challenging place, with constant horizontal winds driven by the massive temperature difference between the two sides, and with the sun fixed permanently on the horizon, never rising, never setting. Then there is the radiation problem we already discussed. Proxima b orbits very close to its star, about 5% of the distance between Earth and the Sun. That means it receives far more stellar wind and flare radiation than Earth does. Every time Proxima erupts, and it erupts often, the planet is bombarded with high-energy particles and radiation. Over billions of years, this bombardment would have likely stripped away any original atmosphere the planet had. Unless Proxima b has a very strong magnetic field protecting it, and we have no evidence that it does, its atmosphere is probably thin, degraded, or entirely absent. Without an atmosphere, there is no surface water. Without surface water, the habitable zone classification becomes essentially meaningless. A planet can be in the theoretically correct temperature range and still be as barren as the Moon if it lacks the atmospheric envelope needed to hold water in liquid form on its surface. We also have no direct imaging of Proxima b, no photographs, not even a pixel. The planet is too small, too dim, and too close to its bright parent star for any current telescope to resolve. All of our information about it comes from indirect measurements, from analysing the tiny wobbles in Proxima's spectrum. We know its mass and its orbit. We do not know its composition, its geology, its atmosphere, or whether it has water. We do not know if it has a moon. We do not know if it has weather. We do not even know for certain whether it is a rocky planet like Earth or a small gas-rich world like Neptune. Mass alone does not tell us everything. So let us be honest about what Proxima b is. It is the nearest possible rocky exoplanet, sitting in the theoretically habitable zone of the nearest possible star. That makes it genuinely exciting from a scientific point of view. But it is also a planet that is almost certainly tidally locked, almost certainly stripped of its atmosphere, almost certainly bathed in hostile radiation, and almost certainly not the Earth analogue that science fiction has been teaching us to hope for. It might have a thin strip of potentially habitable terrain along its terminator. It might have subsurface oceans beneath an icy dark side. It might have some pockets of livability tucked into geological or atmospheric corners we have not yet mapped. But we do not know. And the chances of it being a world where you could simply step out of a spacecraft and breathe the air are, based on what we understand, very low. Which brings us back yet again to the central thread. The nearest star has a planet. But that planet, the destination we might dream of reaching, may not be a meaningful destination at all. Even if we could, somehow, find a way across that 4-light-year gap, what would we find when we arrived? Probably a scorched rock. Probably a thin, damaged atmosphere or no atmosphere at all. Probably a sterile, radiation-battered terminator zone, where the prospects for human survival, let alone for a thriving colony, are dim at best. The destination, in other words, may not be what we want it to be. The fantasy of a second Earth waiting just across the cosmic street turns out to be something much more complicated. Proxima b is a planet. It is real. It is there. But whether it is a place we could ever call home, in any meaningful sense, is an entirely different question. And the early indications suggest that the answer is probably no. The nearest star is not what we think, and neither is the planet orbiting it. Both of them, the star and its companion world, are stranger, harsher, and less hospitable than our imaginations want them to be. Part 12. The True Galactic Structure. And here is where I have to zoom out, because I think we are still carrying around a mental picture of the galaxy that is wildly wrong. Most people, when they picture the Milky Way, imagine something crowded. A brilliant, dense swarm of stars, each one blazing, packed together like the lights of a great city. That is the picture you get from looking at long exposure photographs of distant galaxies, where the apparent density of stars is enormous because the camera has collected light from countless sources and compressed them into a single bright image. But the reality is different. The galaxy is mostly empty. It is vast, yes. It contains somewhere between 100 billion and 400 billion stars, which is an enormous number. But those stars are spread across a disk that is roughly 100,000 light-years across, with a thickness of about 1,000 light-years. The volume is so large, and the stars so comparatively few, that the average distance between stars in our local region of the galaxy is about the same as the distance between us and Proxima Centauri. Let me say that again, because it is important. The average separation between stars in our galactic neighbourhood is about 4 to 5 light-years. That is normal. That is typical. Proxima Centauri is not unusually far away. It is unusually close, relatively speaking, but only because we happen to have a particular stellar neighbour at roughly that distance. If you went to another random point in the galaxy and measured the distance to that location's nearest star, you would probably get a similar number. Stars are sparse. They are not crowded. They are not packed together. They are separated by enormous gulfs of essentially empty space, and those gulfs are the norm, not the exception. Now, there is something even more interesting about the population of stars in our galaxy. The stars you see in the night sky are not representative of what is actually out there. Look up at Orion, for example. You see Betelgeuse, Rigel, Bellatrix, Scythe, all these bright, prominent stars that define the constellation. Every one of them is a large, hot, luminous star. Every one of them is also either very rare in the galaxy or exceptionally distant and bright enough to overcome that distance. The actual statistical majority of stars in the galaxy, probably around 75% of them, are red dwarfs. Small, cool, dim stars like Proxima Centauri. They are everywhere. They are the most common stellar type by far, and almost none of them are visible to the naked eye from Earth, because they simply do not produce enough light to reach us in any perceptible way. So the night sky, pretty as it is lying to you. The sky shows you the unusual stars, the bright ones, the massive ones, the ones that are close enough or luminous enough to burn through the atmosphere and register on your retinas. The sky hides the typical stars, the dim red dwarfs that make up the bulk of the galactic population. If you could see every star within, say, 20 light-years of Earth, the sky would be much busier than it currently appears, and the vast majority of the newcomers would be these faint red dwarfs that you have never noticed. There is a catalogue called RECONS, which stands for Research Consortium on Nearby Stars, that tracks all known stars within about 10 parsecs of us, which is about 33 light-years. The majority of the entries in that catalogue are red dwarfs, many of them at magnitudes well below what the naked eye can detect. Our immediate stellar neighbourhood, the set of stars you could reach within a few decades at light speed, is dominated by these little red stars. The bright showy stars are the minority, even in our own backyard. And this tells us something important. It tells us that the galaxy is not what it appears to be. It is not a crowded swarm of brilliant suns. It is a sparse, mostly empty volume populated largely by dim, small red dwarf stars that outnumber the bright ones by a factor of 3 to 1, spread across vast distances that are typically measured in light-years of separation. Which means that the distance to Proxima Centauri is not an anomaly. It is a statistic. It is a normal result of being a random star in a normal part of a normal galaxy. The universe is full of stars at about this spacing. Everywhere you look, everywhere you could possibly be, the nearest star would be somewhere around 4 or 5 light-years away. That is just how stars are distributed. And this reframes the central thread yet again. The distance to our nearest star is not special. It is not some unusual obstacle placed in our way. It is the normal, expected, typical gap between neighbouring stars in the galaxy. It applies to everyone. Every civilization that has ever arisen, if any others have arisen, has faced the same problem. Every star system is separated from its neighbours by roughly this kind of distance. Every intelligent species, if any others are out there, has looked up at its own nearest star and faced the same wall. The nearest star is not far because the universe has singled us out for isolation. The nearest star is far because the universe is mostly empty, and that emptiness is structural. It is baked into the way matter has distributed itself across space. It is the way things are. And if you think about that for long enough, the loneliness stops feeling like a punishment and starts feeling like a fact. A simple, inescapable, universal fact about what it means to be a thing in a galaxy. Everything in every galaxy lives this way. Every conscious being that has ever contemplated the night sky has contemplated a version of the same gap. The nearest star is not a problem we have. It is a condition we share with every other possible inhabitant of every other possible star system forever. Part 13. Why stars are this far apart. I want to ask a question I do not think we've really stopped to ask yet. Why are stars this far apart? I mean, think about it. The universe is big, sure, but it is not obvious that stars have to be separated by 4 or 5 light years on average. You could imagine a universe where stars were packed more closely together, where the nearest star was only a light month away, or a light week. You could imagine one where they were arranged in dense clusters like beads on a string, so that every civilization was surrounded by dozens of close neighbours. You could imagine all kinds of possible arrangements, but our universe, the one we actually live in, has stars spread out across enormous distances. So why? Is there a reason? And the answer, which is one of the most quietly wonderful facts in all of astronomy, is yes, there is a reason. And the reason, it turns out, is us. Well, not literally us, but life, stability, long-lived planetary systems, the kinds of conditions that allow complex chemistry and eventual biology to emerge. These things require that stars be far apart. Here is why. When stars are too close to each other, their gravity disrupts each other's planetary systems. Planets need stable orbits to support life. Stable orbits require that no large nearby object be constantly pulling on the planet, perturbing its path, sending it off into eccentric orbits, slinging it out into space, or driving it into the parent star. If another star came too close to our Sun, even just a few light months away, the gravitational interaction would likely destabilize the outer solar system, potentially flinging planets out of their orbits, or rearranging the whole system into something chaotic. This does happen, by the way. Astronomers have studied stellar close encounters, and they find that every few 100,000 years or so, another star passes within a few light years of our Sun. These encounters are rare because stars are far apart, and they usually do not cause significant disruption because the approaching star is still too far to affect our planetary orbit strongly. But if stars were much closer together on average, these encounters would happen constantly, and the resulting orbital chaos would make long-term planetary stability impossible. Life, in whatever form, needs long-term planetary stability. Life takes a long time to develop. On Earth, it took something like 4 billion years for complex multicellular life to emerge, and another 500 million years for intelligence to appear. That is a very long time to maintain stable conditions on a planet. If the orbit of that planet were being constantly disturbed by passing stars, the climate, the seasons, the distance from the Sun, all of it would be in constant flux, and the stable background needed for biological evolution would never establish itself. So there is a kind of cosmic trade-off at work. You can have close neighbours, or you can have stable planets, but you cannot really have both. A galaxy where stars were densely packed would be a galaxy with lots of opportunities for stellar interaction and stellar collision and orbital chaos, but very few opportunities for life to evolve on stable worlds. A galaxy where stars are far apart, like ours, is a galaxy where close neighbours are rare, but stable planetary systems can persist for billions of years, giving lifetime to develop. This is why stars are the distance they are. Not exactly this distance, of course. The average spacing of stars is a result of a lot of different processes, including the physics of star formation, the dynamics of the gas clouds that give birth to stars, and the way galaxies as a whole have evolved over billions of years. But broadly, the spacing we observe is the spacing that allows planetary systems to be stable over long timescales. Any galaxy dense enough for civilizations to have lots of close neighbours would probably not be a galaxy where civilizations ever got to exist in the first place. There are exceptions, of course. There are star clusters, tight groups of stars that form together and remain gravitationally bound for some period of time. In these clusters, stars can be relatively close, sometimes only a fraction of a light year apart. The Pleiades is a famous example, though its stars are still spread out over several light years. Even denser clusters, like globular clusters, contain stars packed into volumes so tight that the average spacing is dramatically smaller than in the galactic disk. But those dense environments also appear to be hostile to long-term planetary stability. We have found very few planets in globular clusters, and the ones we have found are often in unusual orbits that suggest they have been disturbed over time. So the empty space between stars is not a bug. It is a feature. It is the thing that allows life to exist at all. If Proxima Centauri were much closer to us, if it were, say, half a light year away instead of 4.2, its gravity would be pulling constantly on our outer solar system. Over billions of years, that pull would have destabilized our planetary orbits, potentially ejecting Jupiter or Saturn, potentially sending comets raining down on the inner planets, potentially making Earth itself uninhabitable. The distance to our nearest star is, in a very real sense, part of the reason we're here to talk about it. And this is where our central thread takes one of its most unexpected turns. The distance that seems like a barrier, the gap that prevents us from reaching the nearest star, is also the structural condition that allowed us to exist in the first place. Isolation is not a punishment, it is a prerequisite. The universe, in its profound indifference, has arranged itself in such a way that conscious observers can only arise on worlds that are too far from their neighbours to easily reach them. The same distance that makes exploration impossible is the distance that made the explorer possible. That is not a contradiction. That is a physical truth. We are here because of the gap. And the gap is the thing we cannot cross. Part 14. Physics as a causal fence. So we have talked about why stars are far apart. Now I want to talk about why distance itself matters in the way that it does. Why we cannot just build a faster ship or a cleverer signal and bypass this problem. Why the 4 light-year gap is not just a practical obstacle, but a structural feature of reality. It comes down to the speed of light. And the speed of light, as I have hinted at before, is not really a speed in the normal sense. It is a property of the universe. It is the speed at which causality itself propagates. And understanding this, I think, is the key to understanding why the nearest star is truly, permanently beyond our reach. Let me try to explain this as simply as I can. In everyday physics, if something happens in one place, like you clap your hands, the effects of that event spread outward at some speed. The sound of your clap travels through the air at the speed of sound, about 340 meters per second. The light of your hands moving travels at the speed of light, much faster. Any gravitational effect of your hands moving, if we could measure it, would also travel at the speed of light because gravity, like light, is part of the fundamental structure of space-time. Now here is the key insight. The speed of light is not just the speed at which light travels. It is the speed at which any cause can affect any effect. It is the speed of causality. Nothing, literally nothing, in the universe can cause anything else to happen faster than this. If you do something, the fastest that the consequences of your action can propagate outward is the speed of light. Anything beyond that horizon is causally disconnected from you right now in this moment. This is what relativity teaches us. Space-time has a structure, and that structure includes a limit on how fast information and causation can spread. This limit is not arbitrary. It is not just something the universe happens to have. It is built into the mathematics of how space-time itself works. You cannot violate it without breaking the consistency of physics. If information could travel faster than light, You could set up situations where effects precede causes, where you could know the outcome of an event before the event occurred, where you could send a message to your past self and change the future. These situations are not just paradoxical, they are incoherent. They cannot exist in a universe that makes sense, so the universe has a kind of fence built into it, a causal fence. And the fence says that any 2 points in space-time can only influence each other if the distance between them is less than the speed of light times the time between them. Everything inside that fence, within the cone of events that you can reach by travelling at or below the speed of light, is part of your causal future. Everything outside that fence, beyond what light could reach in the time available, is not. It is not accessible to you. It cannot be affected by you. It cannot affect you. It is, in a deep physical sense, in a different universe right now. This is called the light cone structure of space-time, and it is one of the most important concepts in modern physics. Every event in the universe has a light cone, a region of space-time that represents the events that could possibly have caused it, and the events that it could possibly cause. And every observer has their own light cone, their own set of events they can reach with a signal, and events that can reach them. What this means for the nearest star is this: Proxima Centauri, right now, at this moment, is outside our current causal cone. We cannot affect it. We cannot be affected by it. Anything happening there right now is, from our perspective, in a disconnected reality. We can only be affected by what happened there 4 years ago, and we can only affect what will happen there 4 years from now. The now of Proxima is outside our reach, permanently, structurally, by the very geometry of space-time. And this is why distance and time are really the same thing in physics. When we say Proxima is 4.2465 light-years away, we are saying that the distance between us and Proxima in the geometry of space-time is equivalent to 4.2465 years of time. Distance and time are two faces of the same underlying structure. They are not separate quantities that happen to be related. They are the same quantity, viewed from different angles. And this, I think, is the deepest answer to the question of why the nearest star is so far away. It is not far because of some arrangement of matter that could have been different. It is not far because of some accident of galactic evolution. It is far because distance, in this universe, is a measure of causal separation. And 2 points that are separated by any distance at all are necessarily separated by some amount of time as well, because the universe enforces a minimum speed at which influence can propagate. In other words, the nearest star is bound by causality itself. It is held at a distance not by space but by the rules that govern how space and time relate to each other. And those rules, as far as we can tell, are not negotiable. They are not engineering problems. They are not things we can overcome with cleverness. They are features of the universe that we inhabit, built into the fabric of reality at a level deeper than matter, deeper than energy, deeper than any of the objects we might want to manipulate. If you wanted to reach the nearest star instantaneously, you would need to violate causality. You would need to break the structure of space-time itself. You would need to exist in a different universe, one with different rules, one where effects could precede causes, and where information could travel at any speed it liked. That universe is not this one. So the nearest star is not just distant. The nearest star is held at a distance by physics. By the same physics that lets electrons form atoms, that lets atoms form molecules, that lets molecules form you. Change that physics, and you do not just get faster travel. You get a different universe entirely, one where you probably do not exist to want to travel. This is the causal fence, and it surrounds everything. Not just Proxima, not just our galaxy. Every star, every planet, everything in the universe is surrounded by its own causal horizon, its own light cone, its own reachable region of space-time. We live inside our little bubble of causally accessible reality. The nearest star lives inside its own bubble. The two bubbles overlap only in the past, in events that are more than 4 years old. They do not overlap in the present. They cannot structurally overlap in the present. Part 15, final collapse of intuition. So here we are, at the end of this long journey around a single number, 4.2465 light-years, the distance to the nearest star. Let me ask you something. Does that number still feel like a distance to you? Does it still feel like 4.2465 units of something, a mileage marker, a measurement of how many meters or kilometers or miles separate us from Proxima Centauri? Because I hope, by now, you have started to see it differently. I hope you have started to see that the number is not really a distance at all. It is a time. It is 4.2465 years of time, laid out across the geometry of space-time, marking how far we are from Proxima in the only unit that really matters at cosmic scales. We are 4 years away from the nearest star, 4 years of delay, 4 years of signal transit, 4 years of causal separation. Think about what that means. We are not located, in any meaningful sense, at a specific point in space and time. We are embedded in a four-dimensional structure called space-time, and our position in that structure is defined by the times and distances to everything around us. And those distances and times are not independent. They are woven together. They are the same thing, seen from different perspectives. So when we say Proxima is 4 light-years away, we should also be saying Proxima is 4 years away. And both of those statements are true, and both of them describe the same thing. The 4 light-years of distance and the 4 years of delay are not two separate features of Proxima. They are one feature, described in two different languages. And this, at last, is the collapse of intuition I have been building toward. The word nearest, when applied to Proxima Centauri, does not mean what we think it means. It does not mean close in the sense of reachable. It does not mean close in the sense of immediately present. It means close only in the sense that the causal separation between us, and it is smaller than the causal separation between us and any other star. It is nearest in relative terms, not in absolute terms, and even that nearestness is enough to place it permanently outside our ability to visit, to communicate with in real time, or to experience as a present object. The opening contradiction, the one we started with, now looks different. Proxima Centauri is 4.2465 light-years away. That is still true. The number is still small in one sense. It is still the smallest number we get when we measure distances to stars. But the smallness of the number is misleading, because the smallness of the number does not translate into closeness in any meaningful human sense. 4.2465 light-years is, for all practical purposes, just as far as 40 light-years, or 400 or 4,000. The physics that forbids us from reaching Proxima is the same physics that forbids us from reaching much more distant stars. The wall is not higher for farther stars. It is the same wall. It is just further away. So the nearest star is a limit. It is the closest expression of a universal boundary, the closest point at which the rules of space-time assert themselves in a way that humans can feel. Beyond Proxima, every other star is just a variation on the same theme. The wall exists at every distance. The wall is reality itself. I want to go back for a moment to the philosophical implication of all this, because it changes something fundamental about how we think of the universe. Most of us, most of the time, carry around an intuitive sense that the universe is happening all at once, that there is a single, shared, flowing, present moment that extends across all of space, that everything that exists right now, together. This intuition is so deep, so automatic, that we barely notice it. It is the default assumption of common sense, but relativity tells us this is wrong, or at the very least it is an illusion. There is no universal now. There is no cosmic moment of the present that extends across all of space. The now you experience is strictly local. It applies to you, here, in your specific place, at your specific velocity. It does not extend to the moon, or the sun, or Proxima Centauri, or anywhere else that is not right here. And it cannot be extended because any attempt to synchronize clocks across distance requires signals, and signals take time. So the universe we live in is not a single flowing now. It is a patchwork of local nows, each one belonging to a particular observer in a particular place, and each one connected to the others only by delayed signals that take years or centuries or millennia to cross the distances between them. Proximity does not guarantee shared time. The nearest star, for all its nearness, exists in a separate now from ours, a now that is 4 years and 3 months different from the now that we inhabit, and that difference cannot be closed. This is a profound thing to realize. It means that existence itself, at the cosmic scale, is not what we intuitively think it is. We're not all living in the same present. We're all living in our own local presence, sending delayed messages to each other, hearing only the echoes of what other parts of the universe were doing long ago. The universe is not a stage where everyone performs simultaneously. It is a vast distributed system where every actor is on their own clock, and the only way to coordinate is to accept the delays. And here is the final reflection I want to leave you with. We're not alone in facing this constraint. If there are other civilizations out there, other minds looking up at their own nearest stars, asking the same questions we're asking, they are all bound by the same rules. Every intelligent species in the universe, wherever they are, faces this same wall. The speed of light is universal. The causal structure of space-time is universal. The distance between stars is on average universal. Whatever beings have ever contemplated the night sky, on whatever planet, have contemplated a version of this same problem. And none of them, as far as physics allows us to say, have ever solved it. That is not a depressing thought to me. That is a strangely unifying thought. We are not uniquely isolated. We are not specially cursed with this particular distance. We share this condition with every possible other mind in the cosmos. It is our common inheritance. It is what it means to be a conscious thing in a universe governed by these laws. And the emotional tone, the feeling that I want you to leave with, is not fear. It is not despair. It is quiet realization. A kind of settled understanding. We live in a universe that has placed us at a particular location, surrounded by a particular cosmos, under a particular set of physical rules. Those rules include a fundamental delay between any 2 points that are separated in space. That delay is not malicious. It is not a cruelty. It is simply how things are. And inside that delay, inside the vast, patient, eternal gap between our world and every other world, we do what we can. We build telescopes. We decode the ancient light that reaches us from distant stars. We imagine what those other places might be like. We send occasional signals into the void, not really knowing if anyone is listening, not really expecting an answer in any time frame that matters to us. We inhabit our local now, and we share what we can of it with each other, and we try to understand the universe by assembling the delayed messages it sends us. The nearest star is not far away. The nearest star is just never now. It exists, yes. It is real, yes. It shines, it flares, it spins, it holds its planets in their orbits, it does everything a star does. But it does all of this in its own time, separated from our time by the 4.2465 years of light travel between us. It is not a place we can visit. It is not a mind we can speak with. It is not a present we can share. It is a set of old photons arriving in our telescopes, bringing us postcards from a world we will never touch. And yet, knowing all of this, feeling the full weight of this separation, I still find myself walking outside at night and looking up. I still find myself pointing toward the southern sky, toward the Alpha Centauri region, knowing that somewhere in that patch of stars hiding behind the brightness of its larger companions is a small red dwarf that I cannot see. And I still find myself marveling at the fact that we know it is there, that we have measured it, that we have reached out with our minds, if not with our ships, and we have mapped the geometry of our nearest piece of the universe. We cannot go there. We probably never will. Our children and our grandchildren probably cannot go there either. The rules of physics, as we currently understand them, will not let us. The causal fence is real. The light wall is real. The 4-year delay is not going anywhere. But we know about it. We understand it. We have figured out what the sky's hiding, and we have written the number down, and we have looked at the number, and we have let the number change us. And that, I think, is the real miracle of all this. Not that we can reach the nearest star. We cannot. But that we can know it. That we can measure it. That we can describe it with enough precision to understand exactly how unreachable it is. The universe has placed its nearest neighbour behind a wall of time that no physics we understand can ever open. But the universe has also given us the minds to see the wall, and to study it, and to understand what it is made of. And there is something quietly magnificent about that. Not that we have conquered the universe, we have not, but that we have come to know, in enormous and patient detail, the exact shape of our own smallness. We are small creatures on a small planet, orbiting a medium-sized star, in an average part of a typical galaxy, embedded in a universe of incomprehensible scale and strangeness. And the nearest of our cosmic neighbours, the closest thing to us that is not us, sits forever just beyond our reach, visible only as a 4-year-old message, silent in its own present, surrounded by the same rules of physics that keep us anchored here. The nearest star is not far away. The nearest star is just never now. And that, I think, is the most strangely beautiful thing the universe has ever tried to tell us. We're not alone in the dark. We're just alone in our moment. Every star that exists in its own moment, and the only way we will ever know each other is to accept the delay, to read the old letters the universe sends us, and to send our own letters out into the dark, knowing that whoever receives them, if anyone does, will be receiving them long after we're gone. That is what it means to be here. That is what it means to look up. That is what it means to share a universe with other worlds, separated from them by distances that are really times, and by times that will never align with our own. The sky, when you understand all of this, does not look smaller. It does not look more remote. It looks instead like what it really is. A record, a memory, a slow, patient, 4-dimensional conversation between everything that exists, conducted at the speed of light, which turns out to be much slower than it sounds when the distances get large enough, and we, tiny as we are, temporary as we are part of that conversation. Not as travellers, not as visitors, as listeners, as readers of the old mail, as the latest in a long line of minds that have looked up at a sky full of ancient light and tried to understand what it was saying. The nearest star has been sending us its light for as long as we have had eyes to see it. Every photon we catch is a small gift, a small ancient message, a small piece of a star that cannot come to us and that we cannot go to. We have each other only through these delayed whispers, and even that, given everything we have learned tonight, is more than the laws of physics had to allow. So the next time you go outside at night, I want you to look up. I want you to find the direction of Proxima Centauri, if you can, using whatever star map or app you prefer. I want you to point toward that invisible little red dwarf, hidden beyond the brightness of its louder companions, and I want you to remember that the light you would be seeing, if you could see it, left that star more than 4 years ago. That star's present is not your present. Its now is not your now. But it is still there. Still shining, still flaring, still holding its planets in their orbits, and we, against every reason to expect otherwise, know about it. We have found it. We have measured it. We have understood what it is and what it is not, and why. The universe made the nearest star unreachable, but it also made us small and patient, capable of knowing that. And that, friends, is the quiet miracle at the centre of everything we have talked about tonight. We cannot go to the stars, but the stars come to us in their slow, ancient, delayed way. And we, for the brief time we are here to see them, get to listen. Thank you for walking through this with me. Thank you for letting the number 4.2465 become something more than a number in your mind. And thank you for being the kind of person who looks up and wonders and wants to understand. The nearest star is not far away. The nearest star is just never now. And we, somehow, are the ones who figured that out.